All right, how's everybody doing on this Thursday? This Physics Friday, Thursday, or whatever. Are you okay? You're surviving? We're almost there, you know. It's going to be over before you know it. So whatever we cover today is on the exam in a week, but I will let you know sort of exactly what that cutoff point is and what you can expect from this chapter. I will tell you that this morning for the 8 o'clock class, I got stuck in traffic. So I was late, and quite a bit late, which means I was only able to cover so much. So you're going to get the same class they got, which means you're going to get a shorter class. So maybe that makes for a better Thursday. So we'll go as far as I made it this morning, and then we'll stop. I won't tell you exactly where that is, though. It'll come when you least expect it. Let's see. So Tuesday, we'll have a review day, going back to like chapter, I think I called it 5B, was where the second exam will pick up through whatever we cover today. So we'll do some review on Tuesday, have an exam next Thursday, and then it'll be break time. Break is good. We'll all miss each other for a whole week. Actually, it's closer to 2 weeks, like 12 days or something in between classes. And then 3 weeks of class remain after that. And we'll be done. Wow. Did I see a question over here? Like a hand? Yeah. I will post whatever we do on Tuesday, which will involve some type of a bit of a guide. Yeah?
Do you know when our Friday will be? It's on a Saturday, I think.
This one is on a Saturday?
I think so. December 15th.
That sounds right. So we'll have class on the 13th, and then 2 days later, we'll have our exam. Great, yeah. Is that the first day of finals? Maybe. If so, you'll get it out of the way. That's good at least, I guess. Yeah, okay, so that should be the first day of finals. Does anybody remember if we have the 8 o'clock exam or like a 10:30-ish or something? It's in the afternoon? Okay. I thought it was late morning, but I'll look it up again. We'll figure it out between now.
Probably not late morning because I know I have another final in the morning.
Let's hope there's no issue. All right, so today we are going to pick up this discussion of momentum. Let me review just a little bit of what's on this slide. Yeah, question?
The format for the second exam is going to be the same as the first.
Same format. Same format, almost exactly. Give or take a few problems, but the same basic idea. Yeah.
Sorry.
No worries.
If you're reviewing anything from yesterday, can you go a little slow?
Go a little slow? For which part?
More towards the beginning, not so much the plugging in the math, not so
Okay.
much the math, but
Okay.
the basics.
Yeah. So let's see. A few things that you should remember from this slide, and I won't review the problems in the middle. Momentum, first of all, is a vector. Vectors, boo, we don't necessarily like vectors. You have to do a little more math when it comes to vectors. It is equal to mass times velocity. Mass times velocity. Remember, something more massive is going to be harder to stop. Something with more velocity is going to be harder to stop. Multiplying those two things together is what we call momentum. The key to using momentum is that they're always going to be around some collision, one item running into another item, things interacting with each other in a way that we ignored before. We always ignored it when one object eventually touched another object and actually collided with it. We cut off those parts of the problems before. You will use momentum during collisions, and I will give you a little bit of info, a lot more detailed info about collisions later today. So you need to be careful with direction because it's a vector, so plus, minus, maybe an angle. Oh, hands went up simultaneously. What happened? Oh, yeah? I wanted that to happen. That's what happened. How about there we go. Not even sure how I got to that button accidentally. Let's see. So be careful with direction. Let me add to that, you're going to be dealing with multiple objects often. So when dealing with momentum, since it's a vector, you have to deal with a vector sum, which means components, addition of vectors, all that type of stuff again, all right? The one other thing we should go back and say here is that since we're dealing with a collision, collisions happen fast. They happen very fast. Like things are not touching each other and then all of a sudden they do and then they're not anymore. Okay, the collision starts and finishes really quickly. So when we're dealing with how much momentum change there is, it's going to be a tiny little sliver of time between what you call initial and what you call final. So close together that like you can't even write them close enough together on your page or in your diagram. They're like practically on top of each other with maybe like microseconds in between. Okay? Do we have any thoughts or questions so far? Feel okay? All right. So let me do this. Change in momentum. Change in momentum is important. Okay? So first of all, it leads us back to something we learned about before, Newton's second law. So we know Newton's second law. We know it as sum of forces equals mass times acceleration. Force and mass are vectors. But it turns out there's a couple of problems with this equation. You're thinking like, ooh, problems with Newton's second law? That doesn't sound like something we should have. We shouldn't have problems with Newton's second law. First of all, in this equation, the mass has to stay the same the entire time. Otherwise, I can't use this equation. So this requires constant mass. If you think back to every problem we've done, we had an object, it had a mass, and it just had that mass the entire time. Forces acted on it, it sped up, it slowed down, things happened, but its mass never changed. Nothing ever like fell out of those boxes that we were dealing with that are sliding up and down inclines. Nothing more complicated than a constant mass was always there. So if you want to do things that are a little more advanced, this is going to hold you up. So for instance, sort of an extreme case would be a rocket. For a rocket, most of the mass is fuel. So as soon as you launch the rocket and it starts burning fuel, the mass begins to drop rapidly. It's not just one of these things where it's like over, days and days and days, maybe the mass changes, but like literally each second, the mass is changing a lot, which I don't know how to deal with that in this equation. We're stuck. So if you want to do rocket science, anybody? No rocket scientists? It turns out rocket science, like people use it as an example of like the pinnacle, like what are you, some kind of rocket scientist? Like, don't think of it as something that's that terrible. It's complicated, but not very much beyond what we're going to do in this chapter, actually, okay? We're not going to do rocket science, you don't have to worry about that. But if you were going to, this version of Newton's second law would not suffice, all right? Another thing that I should tell you is that this particular form is not the original. And this time I'm not lying to you like I did over here with the P and the momentum, that was all made up. This time I'm actually going to tell you that there is another form of Newton's second law which was actually the original, more powerful version that was in Newton's writings. He didn't write down F equals ma, even though that's what we all learned, okay? Instead, the original, more powerful version looks like this. The sum of forces is equal to the change in momentum over the change in time. So this whole thing on the right-hand side is the rate of change of momentum. How fast is the momentum of the object changing? That relates back to the forces that are acting on it. And you'll notice, hiding right inside there, is this delta P that we were dealing with on the previous slide. That's part of why it's so important that we started out like almost immediately talking about change in momentum, not just momentum itself. It lives inside Newton's second law. Now, if you're thinking, okay, you said this is the sum of forces, and that is equal to the sum of forces, those two things have to essentially be the same. How are they related to each other? Let's write this out a little bit further. So I could say that this is equal to P final minus P initial over delta T. So the change in momentum, we can expand that out. And then we know momentum is mass times velocity. So let's plug that in everywhere we see it. So this would be the final mass times the final velocity minus the initial mass times the initial velocity all over delta T. What are these colors I chose for this slide? I don't know. They're not doing it for me. I don't like this. Is anybody like, yes, these are my two favorite colors? Yeah, see, I didn't think so. I should switch to something else, but that's just going to make it worse at this point. So this shows the full power of the equation, right? I've got two different masses in the equation and two different velocities. So you've got a lot of options that can happen there. But this is still not the same as what we had up there. So let's put this restriction on it. In other words, we're taking the powerful equation and putting a little requirement. We're sort of putting it into a box, and we're going to say, what if M final equals M initial? We're saying it's a constant mass. So what if it just so happens in your problem that you do have a constant mass instead of a changing mass? What happens to the equation then? So then I could write this as just mv final minus mv initial over delta t. Now we're just saying all the masses are the same. And then I can factor out a mass. And then v final minus v initial is delta v. And then what is that? Delta v over delta t. That's acceleration. And then yay, we get back to the more simplified version. Okay? So you can take the powerful version and then apply it to things that do have constant mass, and you just end up with MA once again. Okay? So Newton's second law, this is the bigger, more powerful version, but let's take this delta P once again. This is just arrow day apparently. And go over to the next slide. And it turns out that delta P is given a name of its own. Okay, the change in momentum. Instead of always calling it change in momentum, we could just call it impulse. Impulse is equal to the change in momentum all by itself. That numerator on the right-hand side of Newton's second law is a quantity all to itself. So if I were to think about this just a little bit, the change in momentum then must be equal to the sum of the forces times delta t. If I go back and rearrange Newton's second law, so go back over here, multiply the delta t up on the other side. Impulse is the sum of the forces times the amount of time over which those forces are acting. And we're going to make a little simplification here. And I think you'll like this because it gets rid of the calculus. Unless you just want to do the calculus. I don't hear anybody screaming for calculus, so okay, we'll leave it out. Let's think about a collision. Any baseball fans? Any baseball haters? Was that a baseball fan, maybe a little bit? Yeah. I grew up loving baseball, and I just sort of drifted away from it over the years. I don't know why. Somewhere in my parents' attic are like 30,000 baseball cards. That was my childhood. And then occasionally they like to joke. They're like, hey, we sold your baseball cards. And I'm like, no, you didn't. And then we sold them. I'm like, they're not worth anything. No, we sold them again. Like, no, you didn't. So they're still sitting there. I collected baseball cards during a time where they were overly mass produced, so they're literally not worth anything. They're just sitting there as a part of my childhood, taking up space. And I keep thinking someday I'll go back and revisit my childhood and just flip through 30,000 baseball cards and be like, oh, I remember when I was 6. I bought this, and I remember looking at that picture, and life was, yeah, I was a baseball fan. But let's think about what happens in the game the entire time. Pitcher throws the ball, batter hits the ball, right? There is a massive collision that happens at the middle of that. Think about a baseball that's moving extremely fast one direction, and then all of a sudden it's like, boom, going really fast the other direction, even faster the other direction. That collision between bat and ball doesn't take very long. It's just a split second, but a lot is going on during that split second. You might imagine that there must be some forces coming from the bat on the ball, and then according to Newton's third law, some forces from the ball on the bat. But there's a lot hiding in there that's really hard to sort of take apart and analyze. So if we were to, say, make a graph of, let's say, this is the force from bat on ball, and look at that as a function of time. And let's say that maybe right here at t equals 0, the ball is thrown. And then maybe we're just in the ball, just like we're a force detector, just waiting to see if we feel anything happening to us besides gravity. So maybe we're just flying through the air and it's like, I don't really detect anything, nothing's hitting me. And this is our little force detector. Time is going by, the ball is flying through the air, and then all of a sudden, bat comes along. And what happens to my graph? Well, the force goes from 0 to just like, whee, and then it goes away again. Okay? It's like I experience all this force, and then all of a sudden I don't experience any force again. So this should go back to 0. My apologies. Okay? Force from bat on ball. It's non-existent until it is, and when it is, it's ridiculously high. So you can imagine this is a very large force and a rapidly changing force. It's not a constant value. It's not like there's just one force that's being applied to the ball and it's over. You can even imagine like maybe as the bat just begins to strike the ball, like there's a little bit of force and then it pushes into the ball even farther, and the force grows and grows and grows and grows and then goes back to 0. If you've ever looked at slow motion footage of a bat striking a ball, you start to get the idea that the forces must be really, really large because the spherical ball doesn't stay spherical. Like during this collision, it actually gets sort of smushed and deformed, and then once the force is over, it goes back to a spherical shape. If you've ever seen slow motion footage of a golf ball being struck, and a golf ball is even harder than a baseball, it does the same thing. Like it kind of flattens a little bit during the collision. It takes a lot of force for that to happen, okay? A lot is going on during the collision. So when these forces are at play from here to here, this is delta t. This is the collision time. Collision time. The period of time when the forces are occurring, whatever that force may be, which clearly it's kind of hard to tell exactly what it is, it's sort of all over the place, is our collision time. Now, take a look at the equation up above. Force times delta t gives me impulse, or change in momentum. Notice what I've graphed. Force and delta t. That means that if we were to think of this from a calculus standpoint, which we're not going to do beyond what I'm about to say, if I could find this area, the area under the curve, that is the impulse. The impulse or the change in momentum is given by that area under the curve. So if I had some sort of apparatus, say in the baseball, that can detect the force and actually give me a graph of how the force changes as a function of time, you could plug that into something that can do the math and calculate the area under the curve, and you can find out exactly how much the momentum of the baseball changed. Those are experiments you could probably do with just ordering a few little pieces of equipment and be done with it, okay? Not a terribly difficult experiment. The calculation might be a little harder. So here's what we're going to do. We are going to simplify this like so. We're going to say that impulse, or delta P, is just equal to the average force times the collision time. So instead of looking at all the different values of the force that are growing and decreasing, I'm just going to go to like right here and just roughly say like, that's probably about what the average is. Maybe a little less than halfway up, okay? That is the average force. And now if I'm multiplying average force times delta T, what I'm actually calculating is an area that looks something like this. If I look at those two times, I'm finding all of this area. So that area equals impulse. And if you just look at the two areas, the area in red and the area in green, they're roughly the same. It's at least a reasonable approximation. You might imagine like I could split this top area up and like take half of it and fold it down into here and take the other half and kind of fold it down into there, and I'd get roughly about the same area, okay? So doing this is a reasonable approximation and it saves us a whole lot of calculus work. Instead of dealing with the area of this peak, I can just take the area of a rectangle, and that's nice and simple, okay? Force average times delta T. Before we get to the next few slides, does anybody want to stop me? You're like, yeah, I want to stop you. That's mean, don't talk like that. I'm talking to myself again today. I gotta stop putting words in all your mouths and just having a conversation. Maybe I'm doing it because you won't talk. Please talk. Say things. Ask questions. No, nothing? Okay. You're thinking like, I wonder how far in the slides he's gonna go. So you're just being like extra quiet to see if I get there quickly. Yeah.
I don't really want to ask the question.
Okay.
Like, so I guess like when the bat hits the ball, and then like you calculate the impulse, is that like the would that be like the impulse of the whole system, or the impulse on just the ball, or just the bat, or what?
That would be two things. That is both the impulse on the ball and the impulse on the bat. Because
So
of
they
Newton's
have to
third law, they have to be exerting the same force on the ball.
Okay.
Okay? Both. Anyone else?
What is that? Under if happens that I need not
This one, this area?
This is the-
Oh, there.
Yeah,
So it's
area.
gonna be-
That is a terribly written area. Let's try that again. A-R-E-A. There. Maybe that looks better. Maybe it doesn't. The green area there is equal to the impulse as well. So let's see. A few multiple choice questions, and then we get to what is the meat of this chapter. What is the, or if you're a vegetarian, what is the veggie of this chapter, I guess we could say. Interesting expressions. So, a system of particles, a bunch of objects, is known to have a total kinetic energy of 0. So we know that kinetic energy is equal to 1/2 mv squared. If all of those objects have a kinetic energy of 0, what does that tell me about the velocity? Yeah, all of them have to have a velocity of 0. That's the only way I can get 0 for all of the kinetic energy. However, what does that imply about the total momentum of all of those objects? Thoughts? If the velocity of all of them is 0, what will the momentum of all of them added together be?
It has to be 0 because they're not moving.
Yeah, none of them are moving. They have to have total momentum equal to 0. Good. But what if I flip it around? Now we know that the momentum is 0. What does that tell you about the kinetic energy? I know you want to just be like, same thing. But clearly it can't be the same thing, because why would I ask? So what's the difference? What's going on here? Does that help at all? Or did I just write two random words that seem to not matter in any way? Can I get a total momentum of 0 with objects that are moving? Yeah. So maybe, what if I just had two masses that are the same and have velocities that are the same but in opposite directions? Ooh. In that particular case, the total momentum is equal to 0, right? However, they're both moving, they both have kinetic energy. So there's kinetic energy here equal to 1/2 mv squared, and there's kinetic energy here equal to 1/2 mv squared. So you can have kinetic energy, but still have zero momentum. Okay, kinetic energy but zero momentum. So does it necessarily follow that the total kinetic energy of the system is also zero? No. And it's highlighting the difference between a vector quantity and a scalar quantity. Momentum is a vector. Let's see. We are not going to do this one. I'm going to skip several of these today. I do want to do this one. I'll give you a chance to read and vote a little bit. I think you have the answer. Feel free to share it with me. I'd love to hear it. You all ignore me. I'm so good at that. He's weird, but he doesn't exist. I am weird. You're not even yes or no, yes. You exist. Rate of change of momentum. That is the entire right side of Newton's second law. Delta P over delta T. What do you think? Greater than, less than, or equal to? Anyone vote greater than? Less than?
I say less.
Less than? Several less thans? Equal to? Some less thans and some equal tos. Not a lot of people are going for greater than. Okay, I'm going to go ahead and cross off greater than. I will agree that that's not an answer. So let's see. Net force of 200 newtons acts on both of them. They're both experiencing the same net force. So this side of the equation is the same. And let's see. It doesn't really tell us anything else other than them having a different mass. But that's sort of like buried down inside the momentum. You can imagine the mass is hiding in there, and we know that that's different. However, it's not asking me about the momentum. It's not asking me about the time. It's asking me about this entire right side of the equation. And I already know they have the same left side of the equation. Don't think too much farther. If the left side is equal to the right side and they have the same left side, they have to have the same right side. Okay? So these are equal to each other. They still have the same rate of change of momentum. If that bothers you a little bit, they don't necessarily end up with the same velocity. Remember, it's mass times velocity, right? So the one with less mass is going to end up with more velocity, but it all comes together to be the same amount of momentum. Okay? So let's see, what about this one? It's asking a similar question. See if you get to this answer a little faster. Heavier one, lighter one, both the same. So they have no initial momentum. It says both of them are at rest. They tell me that they experience the same force over the same period of time. The only option is for them to have the same final momentum. Okay? So all we're doing in these problems is manipulating Newton's second law, okay, looking at what's changing and what's not. So this addresses the common question, which one has the larger velocity after the force acts? Same force on something that's lighter is going to give it more velocity, but they do have the same momentum. same momentum, but different mass and velocity, okay? Which brings us to this one, which just, I'm gonna get rid of this. It causes problems, and it's not a very good question, mostly because it has answers like get insurance and call your physics professor. And yes, do get insurance, but don't call me, okay? Like, I'm not gonna be able to help you in this situation, so let's just kind of ignore that. And we actually answered this on the first slide of the whole chapter, so we're not gonna do that. Which brings me to the bulk of the chapter. Now, at this point, I will tell you how much we're going to do. We're gonna do this slide. We're gonna do that slide. We're gonna do this slide, and then I'm gonna insert one, and that will be all. That's as far as we're going to make it, because there's a lot on these slides I need to explain. Your question.
So I'm still bothered by the momentum.
Yep.
Is that like kind of related to how like you can drop two objects and they'll both like reach the ground at the same time? Like I'm trying to.
No, that's a different concept.
I'm not.
What part of momentum is bothering you?
Because like, because for the momentum equation, the greater mass,
Mm-hmm.
the velocity would be greater momentum.
Yeah.
So,
So in this particular case, they have the same momentum, which is equal to mv. So think P final is equal to mass times velocity. But mass times velocity are inversely proportional to each other. So I can get the same final velocity with a variety of combinations of mass and velocity. It's just in this particular case, after the force is done, this one's not going to be moving very fast. This one is. But if we had the numbers and we actually multiplied their masses and velocities, we'd get the exact same momentum. I don't know if it's that part that's bothering you or this whole idea of it coming from a force. Don't know? Okay. Keep thinking. If questions arise, ask, or ask after class, or whatever. Okay. Anyone else? In the back.
Can you explain what momentum is?
What momentum, what?
What momentum is?
This is a common question. What momentum is? Let me say two things, first of all. It's theoretical. It's made up. Kind of just like energy. Okay? It's not like a physical thing where I could be like, ooh, velocity. I understand like that thing went so many meters and it took so many seconds to go that far. It's more of a handy mathematical description that allows us to deal with things we observe. I wouldn't think of it as like a physical, like tangible sort of thing that an object possesses. It's something we made up as physicists to help us solve problems using quantities that we can measure. So think of mass times velocity as a made-up quantity that we've observed stays constant when things collide into each other. Okay? Energy is the same sort of thing. Like, what is energy? You know, I mean, yeah, like we can calculate it using tangible things like force and distance, and that we could say is equal to work. But at the end of the day, it's like something where we've combined these multiple quantities together into something that helps us explain the universe, even if it's not really something tangible that we can actually describe. Momentum is one of those, and I can't really give you a better answer than that. It's a good question, and it's a bad answer. And I understand that. Okay? Let's talk about collisions. I'm sorry to leave you with such a sad answer. We made it up. Like, well, why do we have to learn it? It helps you solve problems. Okay? It's a tool. In the last chapter, we had conservation of energy, specifically mechanical energy. This is going to be the second of our conservation laws, meaning momentum, whatever it is, as objects collide, stays constant. The amount of mass times velocity in the problem does not change if you add it all up for all of the things that are colliding into each other. So we can say that this is true if, first of all, the net external force, which we could describe as something like this, is zero. So whatever I've decided is my system, my things that are colliding, if nothing from the outside comes along and exerts a force, then we can say that the momentum of the system stays constant. In other words, if I add up all of the momentum of all the individual objects that are interacting before the collision, it has to be equal to the sum of all the momentum of the objects after the collision. This equation describes conservation of momentum. Okay? Notice we keep referring to the system because we're going to be dealing with collisions. Collisions inherently involve at least two different objects. You can't really collide with yourself. At least I don't think so. Like I don't know, maybe I can trip over my own foot, like that could happen, but a collision with yourself doesn't make a whole lot of sense. So there's always going to be at least two things that are in our system, and we could look at the momentum of each one of those objects and add it together before they collide, and then again look at the momentum of each of those objects after they collide. If you add those together, they will be the same number. The only time that would not be true is if these two objects have momentum and they collide, and then I come along at the exact same time and say, like, shove one of the objects. Like I've messed up the problem. Some work has been done from the outside, and then the momentum will not stay the same, okay? So, as you can see here, right at the bottom, this applies to the system as a whole. You can think of your system as the objects that are colliding. The objects that are colliding. So, collisions. Over on the next slide, we're going to talk about a few different types of collisions. And I'm going to try to, on this slide, describe how you can tell what type of collision you have. And then on the next slide, we're going to deal with all the math that goes into solving problems with those collisions, okay? So first of all, keep in mind that no matter what type of collision we're about to discuss, momentum is conserved in every single case, okay? So you might as well just tie those words together in your head. Collisions, momentum, collisions, momentum, collisions, momentum, collisions, momentum. I think I did that on Tuesday as well. Collisions, momentum, collisions, momentum. Put them together. Momentum stays the same during a collision, okay? And don't forget that, again, a collision is a very brief period of time, so initial and final are going to be very, very close together. These are things that we already know. Let's see. So types of collisions. First of all, the elastic collision. The elastic collision is defined all the way over here by objects that are not deformed by the collision, meaning they're not changed, they're not broken, they're not different after the collision happens. So if you were to go back and think about maybe the golf ball and the golf club, like you can hit a golf ball many times and like look at the golf ball before and after and it's like, oh look, it's still a sphere. Like nothing really changed about the object. Same with the baseball. You might get some light scuffs and damage, which kind of throws this off just a little bit. But in general, the object isn't really deformed in any way. It's not like the baseball is now a pancake. Like it hasn't turned into a very different shape, okay? The objects are not deformed by the collision. In the case of the ball that we imagine dropping to the floor, the bouncy ball, right? It's a ball, I drop it, I look at it again, like, hey look, it's still a ball. It hasn't changed shape, it hasn't been deformed in some way. So some examples here would be the bouncy ball, or if anybody plays pool, billiards, anybody? Yes, no, some of you, yeah, there's always a few in a class that like the game sport. Could it be called a sport? I don't know, okay. That's a classic example as well, right? All of the balls on the table in a game of pool or billiards collide a lot. Look at them before and after they collide with each other. They're all still spheres. They're basically the same before and after. So the bouncy ball or billiards. Okay? Notice, what we're going to use on the next slide mathematically is we're going to say that in an elastic collision, yes, because it's a collision, momentum is conserved. That's always true. But we get this extra help because kinetic energy will also be conserved in an elastic collision. So you should be able to read a problem at this point and be like, ooh, did the objects get damaged in some way through the collision? No, they didn't. I now know it's an elastic collision, and I now know that I have two different equations I'm going to be able to use to help me solve the problem. Conservation of momentum, and just the fact that if I look at the kinetic energy before and after, they're going to be the same values. Okay, those are conserved as well. We're going to deal with the math of that on the next page, right? Number 2 is the inelastic collision. The inelastic collision is exactly opposite to the elastic collision. And I hate all these words because I have to enunciate a lot, because otherwise it's like an elastic collision, which sounds a whole lot like inelastic collision, and then the grammar and the words and everything kind of merges together. So here we have an inelastic collision, all right? In the case of the inelastic collision, the objects are deformed, they're damaged, they're changed, they're not the same anymore after the collision. So for example, if I were to say just all of a sudden run as fast as I can toward that window, me and the window are going to have an interaction, maybe even a collision, yeah? Things are going to happen, and I'm pretty sure that after the fact, if you look at me and the window, after we collide, we're not quite going to be the same anymore, and it's going to be sad. Maybe the glass is broken, maybe my arm is broken, maybe I'm cut and bleeding, like we have been damaged or deformed in some way by the collision, okay? That would be one example of an inelastic collision. Cars crash all the time. Look at cars before and after they crash into each other. Are they the same? Probably not, unless it's an extremely low-speed collision, okay? Typically, there's dents, there's damage, parts are falling off, windows are broken, things have been changed as a result of the collision, okay? So what that does is it changes what is conserved. Momentum still applies, but now kinetic energy is not the same because I lost some. Where did that energy go? It went into breaking things, okay? The fact that the window got broken, my arm got broken, the car got busted, some of the kinetic energy went into like physically mangling the objects, and now that energy is lost. I don't have the same amount of kinetic energy after that I had before. You see the basic idea between the collisions? You could read a problem and be like, ooh, I know what that is. Yes? Just say yes, you can. It's not terribly hard, I don't think, okay? Are the objects damaged or are they not? So let me write a couple of those examples here below. We could say cars, or the other example was me, okay? If I collide with something, I'm probably going to be changed by that collision, unless that collision is, well, not much of a collision, all right? Notice underneath that, we have a special case of the inelastic collision. We'll say that this is a special case that goes by 3 different names, just depending on the textbook you use. It is like the ideal inelastic collision. It's perfectly inelastic, or totally inelastic, or completely inelastic. It's like 100% inelastic, okay? In this particular case, not only are the objects deformed and changed, they are so beaten up and smashed together that they basically become one object after the collision, okay? So in the case of the cars, you can imagine cars that like collide together, and then there's all sorts of like damage and things are mangled, right? So that the cars after the collision are sort of moving as one car chunk together as they slide like off the road or whatever, all right? On the other hand, like what if instead of I decided to run at this window, what if I decided to run at like this sheetrock wall or whatever it's made of with my arms out? Ouch. First of all, what if I demoed everything that I suggested in class? I'd be one sad-looking individual afterwards. So let's say I ran like full speed like this at the wall, and I'm like, ah! Right? And then I end up like buried in the wall up to my arms. I'd say that'd be a totally inelastic collision. Me and the wall would be one, right? I'd be stuck to the wall, and we would just be one like unit at that point, all right? Perfectly, totally inelastic collision. After the collision, the objects are one thing, all right? So let's see, what can we do with all of this on the next slide? Here's where we're going to get into the equations. You will notice I've put up here a 1D and a 2D because we're dealing with vectors. It sort of matters whether things are just acting along one straight line or whether there's an XY plane or even 3D, which we're not going to deal with at all. Let me go ahead, just to make you feel a little bit better. This is not on exam 2. This will be on the final. Okay. Also, I will go ahead and tell you what goes down here. These are the same equations as what we're about to develop above for one dimension. Let's see, I should say as 1D, but separate momentum equations in the X and Y directions. So it's kind of double the work to deal with 2 dimensions, and it gets a lot more complicated really, really fast. We're not going to do even an example with that until actually it'd be after break now. So you don't have to think about that for like 3 weeks or something, okay? So it's going to be the same equations, we just have to deal with it in the X and Y directions at the same time, and that ends up being a whole lot more work. So in one dimension, let's start first of all with the equations that we're going to use for all collision types. For all collisions, conservation of momentum applies. Conservation of momentum says the sum of the momentum initial equals the sum of the momentum final. And let's say at this point we are just going to write equations for 2 objects colliding, which deals with most situations, but you could imagine 3 or 4 colliding at the same time. And you will see when I write the equations, it's really easy to extend this to additional objects if you want to. You're just going to add terms that look exactly the same. But all of them start with this basic idea. All the momentum added up before has to equal all the momentum added up after. So I can expand this out a little bit and say that the momentum initial for object 1 plus the momentum initial for object 2 has to be equal to the momentum final of object 1 plus the momentum final of object 2. Add up the momentum for every object before and after the collision and set them equal. If you have 3 objects, just put another term on both sides. If you have 4, put 2 more terms on both sides, etc., etc., etc. Add up all the momentum before and after the collision and set them equal to each other. Here we're dealing with just 2 objects. So we can expand that out further because we have an equation for momentum, right? So this is going to be mass 1 times velocity initial 1 plus mass 2 times velocity initial 2 equals mass 1 velocity final 1 plus mass 2 velocity final 2. We're just plugging in mass times velocity for each of our momentum. Momentums. I don't know. I think it's momenta. Who cares? So this is our equation for conservation of momentum for 2 objects. Do you follow? Do you see how that came straight out of what I started with at the top? You're like, yes, we do understand. It looks beautiful. Those are very nice equations. We like them, and we fully understand them. Okay, maybe I'm putting words in your mouth again. All right? That top equation, this thing applies for every collision you have. All that stuff we talked about on the previous slide, you can always use the equation we have so far. All right? However, we have some other cases. So what if we have an elastic equation? Or not elastic equation, elastic collision. In an elastic collision, we can say that kinetic energy is also conserved. So we get an additional equation that we can use. We can say that if I add up all the kinetic energy initial, it equals all the kinetic energy final. And we'll follow basically the exact same approach. We've got two objects, so I can say kinetic energy initial 1 plus kinetic energy initial 2 equals kinetic energy final 1 plus kinetic energy final 2. Just adding up all the individual kinetic energies and setting them equal to each other. Which, prepare yourself, each one of those is equal to 1/2 mv squared. So let's write all that out as well. So that's 1/2 mass 1 v1 initial squared. Ugh. It's too many subscripts and superscripts and all is lost. And then we've got one of those for mass 2, so plus m2 v2 initial squared equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And then, yay, that is conservation of just kinetic energy. All of it added up before the collision equals all of it added up after the collision. Everyone still alive? A little bit, maybe, perhaps, okay. So I'm gonna number these two equations because we're gonna use them on the next slide. So this is number 1 and this is number 2. Okay, so just prepare yourself for this next slide. They're gonna go over there, we're gonna do something with them. But let me add one more equation on this slide, and that is if I have a totally inelastic collision. In the case of the totally inelastic collision, well, inelastic, this kinetic energy stuff doesn't apply, but conservation of momentum still does. It's just that after the collision, I no longer have two separate objects. So I can take this exact same equation and say that before the collision, whoops, don't need a half there, I have m1 v1 initial plus m2 v2 initial. But after the collision, they are added together. So the two masses become one, and if they are one object, then they have a velocity that's shared between them. So it's mass times velocity, but now it's just mass times velocity for this one big combined thing. So there's a third equation that you might use. So you've got kind of like this page of options depending on what type of collision you have. Is it any type of collision at all? Conservation of momentum works. If it's elastic, you can add in equation 2. If it's totally inelastic, you can switch over to the equation 3 on the top right. Okay? So you have to read the problem and try to deduce what type of collision you have, and it will lead you to which equations are valid. Whew, we've got one more slide to do. Who's got questions, thoughts, complaints? It's a nice cool breeze coming in from outside today. I'm not complaining at all. Okay, so let me put in this one slide. And I think I like what's coming up next the best of what we're going to talk about today. So let's see. We just came from that previous slide in red, so I will stick with that and say, ooh, there we go. Ooh. We have those two equations, equations 1 and 2. So take equations 1 and 2 and put them together with what we will call much algebra. Algebra we're not going to do. Algebra I'm not going to require you to do. If you decide that you want to do it, expect it to take a while and probably at least 2 pages of work. Okay? It literally is quite a bit of algebra. Because what you can do is take those two equations, right, the 1 and 2 on this slide, and mash them all together and get some equations for the final velocities after the collision, okay? So we're going to get some results here after a lot of algebra. if I do this, if I say that the second mass is initially at rest, another I in there, you can take equations 1 and 2, set V2 initial to 0, and it will allow you to solve for V1 final and V2 final. And I'm just going to tell you what these equations are because, like I say, they are not easy to get to. So M1 minus M2 over M1 plus M2 times V1 initial. So there's an equation for how fast the first mass is moving after the collision. And then to find out how fast the second mass is moving after the collision, we get 2 M1 over M1 plus M2 times V1 initial. Neither one of them has V2 initial in it because remember, it's not moving, it's 0. So we've got these two equations. If one of the masses starts out at rest, so that's kind of a more simplified case, but also you can imagine it happens quite a lot. A car is stopped at an intersection, it's not moving, and another car goes bang and hits it, right? This is the type of equation that might work in that particular case. If you're playing pool, right, often you hit one ball, all the other balls are stationary until you strike them. These equations apply, okay? One object is initially at rest. Now, if you do a little bit more algebra, let's do this. Down to here. This is, like I said, the day of arrows, just arrows everywhere. And in this particular case, if both are moving before the collision, you get one equation that comes out, and I will write it out for you, and then I have to talk about those first two equations a little bit more, and then we'll be done. So you get something that looks like this: V2 final minus V1 final equals negative V2 initial minus V1 initial. Notice on both sides it's like the difference in how fast the two objects are moving. So on the left it's the difference in how fast they're moving after the collision, and on the right I have the difference in how fast they were moving before the collision. So we might say that the relative velocities of the two objects are the same before and after, just in opposite directions. And that's the negative sign. Relative velocities are the same before and after the collisions. They're just in opposite directions, which is given by that negative sign. Okay? This is the third equation that comes out of all that algebra. Have fun if you want to play with that. Good luck and enjoy your Thanksgiving break that's coming up because you'll need it afterwards. All right? Now, let me go back up to these first two equations and see if things make sense. Let's imagine that mass 2 is initially at rest. So let's say mass 2 is just sitting, and just to get rid of all the other forces, imagine we're like in space and there's a mass 2 that's just like sitting here floating. Mass 1 is going to be over here and it's going to run into mass 2. Okay, there's going to be a collision between the two of them. Let's see what happens if mass 1 is much, 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 much less than mass 2. Mass 1 is less than mass 2. So I'm like a little tiny pebble, and mass 2 is a massive boulder. Okay? And then the tiny little pebble is going to run into the boulder that's stationary. What do you think is going to happen?
Mass 1 might move backward in some other direction.
I would agree. Mass 1 should sort of bounce, right? What would mass 2 likely do? It's probably not going to be affected very much. That would sort of make sense, right? So we're assuming mass 1 is much, 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 much larger than mass 2. Take a look at what this equation says, or excuse me, much, much smaller. So if M1s are a lot less, they basically kind of fade away to 0, and then I have negative M2 over M2, which is just negative 1, which just leaves me with a negative sign in here. That's all that's there. So this equation says that the final velocity of the little pebble is negative the initial velocity of the little pebble. It just bounces off with the exact same velocity. Okay, so that tells me exactly what I would have expected. And just to be a little bit more precise, let's not say that that is a hard equal sign. It's roughly equal to negative its initial velocity. Look at this other one. If m1 is really, really small, approaching 0, I've got a 0 in the numerator here. This whole side just becomes 0. The final velocity of the big boulder. Anybody catch what he said? So in this particular case, you're just going to get 0.
Why are people walking out?
It's a good question.
It's the
I have no idea.
It's like
Democrats retain control over the house. Like, what the hell are people so pissed off about?
it's like the 15th anniversary of like
Oh yeah?
that the students walk out for ethnic studies. Today.
I don't
So
know.
people are walking out for that.
If some of you want to walk out, have fun. I'll just keep talking. It's no big deal either way. I'm recording. That's fantastic. So you can always watch it later. So looking at this,
Oh, why did I say that?
why did you say what?
You don't know who you are. Okay, good.
Yeah, I don't know. So anyway, M1, 0. I just get 0 on this side, which means that this big boulder is going to do what we expect. The little one bounces off. The second one just sits here. Okay, so that seems to agree. So that's kind of happy. What if we flip it around the other way, and this will be the last thing that I do today. If M1 is a lot bigger than M2. So now we've got the little tiny pebble that's just sitting here, and a massive boulder decides to run and collide into it. Now what do you think is going to happen? What happens to the big one? Not much, right? It's just going to just sort of blaze right on through and just keep going. I wonder what will happen to the little one, though.
It'll move twice the distance as it moved before when the,
That's close.
or I mean, yeah.
Yes, I think you're thinking the right thing. It's just sitting here. It's going to bounce off and go that direction, but it works out it goes twice as fast as the thing that collides with it, and we can see that from these equations. If M1 is a lot bigger, then the M2s are basically gone. The M1s cancel out, and the final velocity of the boulder is the same as what it was before. It just blazes right on through. So we could say, and let me switch colors here. So we could go down here and say that V1 final equals V1 initial. It's basically unaffected. On the other hand, if I look at this particular equation, and again, M1 is the big one, well, you can look at this and say like, well, this is basically gone, and then the M1s cancel, and I'm just left with a 2, and that's what we expected. So V2 final equals 2 V1 initial. And you get exactly what you think you should get on all of those. Now, with regards to the exam that's coming up, I need to put a little note here at the bottom. Exam, well, that's not how you spell exam. Exam 2 coverage ends here. But prepare yourself for this. You'll notice we haven't solved any problems in Chapter 9 yet. That works out in your favor. But Chapter 9 will only be conceptual. Means I might ask multiple choice questions that involve no calculations. You might have to look at some of these equations and be like, ooh, this is going to happen, like we did in the multiple choice questions, but only conceptual only, so it can only be in the multiple choice. So that means the exam starts at like 5A and goes to sort of like 9A, I guess, if you want to think about it that way. But what we've covered so far in Chapter 9 is conceptual only, and I will post this, including that slide, online, and we're done for the day. Your question?
Will exam 2 have the same amount of questions as exam 1?
Roughly. I can't say it'll be exact, but roughly the same. What should take the same amount of time?
The problems that we're going over on Tuesday, are you gonna have to post that